Hiya, this is a GCSE stream and this is for OCR Gateway. This is a triple science. I'm going to go through a triple science paper just now. Okay, I'm going to do some AQA GCSE stuff tomorrow as well, so if that's for you, then tune in tomorrow. This will still be useful to you whatever exam board you do, because you really want to look at how to solve physics problems, okay, and there's loads of things that will be relevant to paper 2. This is the last little push. I know that you're tired. It's the end of your GCSEs now, okay? But you are ready for this, okay? Just go in there and show your qualities one last time for science. Okay, you can do this. When I go through the questions in the exam paper, then just focus on how I solve the problem, not what the answers are, because the answers won't be the same, but the techniques that we use to solve the problems will be the same in that exam on Friday. If you're A-level and you're looking for help for your exam tomorrow, well, you need to be getting to bed pretty soon anyway, to be ready for that exam tomorrow morning. But also, I've got loads of live feeds I did earlier and loads of links in that to ways you can prepare for your paper 3. Alright, let's go ahead and jump straight into the paper. So here we are. So this is an OCR Gateway paper, and this is what they call paper 4, the higher tier for the second paper, if you like, of physics. Right, let's just jump straight in. So the multiple choice, make sure that you try and answer the questions before really before looking at the answers. So what's the efficiency? Calculate the efficiency, in other words, of the energy loss for the radiator. What's the efficiency and energy loss? Right, okay. So you're told radio transfers 30 joules of potential energy to 27 joules of useful. So efficiency is the useful over the total. So 27 over 30 gives us 0.9 or 90%. Okay, so that's the efficiency, so it's got to be one of these two. And the energy loss, well, we had 30 joules and we've only used 27, so the energy loss is just 3. So the answer is C. A boy kicks a football. Okay, football's got a mass of 400 grams. You know pretty much to convert that straight away. So 400 grams is 0.4 kilograms, and well, what's the it's 0.8 meters, and gravitational field strength is 10. So use the equation. Gravitational potential energy is equal to 0.4 times 10 times 0.8, 3.2 joules. Okay, and that's the answer there. The national grid transfers energy efficiently using high voltages. Why are high voltages more efficient? Just give me one sec. Okay, why are high voltages more efficient? Challenges of live video there. Okay, so high voltages, they produce a lower current because we've stepped up the voltage. This is not the case. It's not V equals IR where voltage is proportional to current. Okay, it's where the power before the transformer is equal to the power after the transformer. So you use this equation, I1 V1 equals I2 V2, and this comes back later. We use a low current, and there's loads in this paper about the heating effect of current. Which statement describes nuclear fusion? Okay, nuclear fusion is light nuclei joining to make heavier nuclei. So 2 hydrogen nuclei join to form a helium nucleus is the answer in this case here. So I think I'm just going to put up with that. Hopefully you can see well enough. Bright enough. Okay, that's very yellow. Which row correctly describes domestic electricity supply in the UK? Well, it is alternating current, it's 50 Hz and it's 230 volts, so we don't even need to go any further than that. That's just a bit of recall for you there. What's a typical weight of an empty single-decker school bus? Okay, now weight is a force, so you need to turn it into newtons. Well, just think roughly, what's it going to be like? Okay, I always think a small car is about a ton. Okay, and a ton is 1,000 kilograms. Yeah, so a single-decker school bus might be like 10 small cars, or certainly the order of magnitude of that, approximately 10 ton. So 10,000 kilograms times by G gives you 100,000 newtons. So it's going to be in the order of 100,000 newtons. 120,000 newtons is the option we've got. How was the sun formed? So the sun, this is about stellar evolution. Sun was formed from dust and gas pulled together by gravity, leading to nuclear fusion. Gas and dust pulled together, nuclear fusion. So be careful with these. Okay, I suggest you go through these one by one and eliminate the distractors. An element has more than one isotope, which correctly describes the atoms of all isotopes in this element. Okay, the number of electrons would be the same, number of protons would be the same, and the number of neutrons would be different. So the only option is C here. The most abundant form of radium is radium-226. Its nuclear mass is 226 and its nucleus contains 138 neutrons, which is an isotope of radium. So basically you can work out the number of protons in radium by taking the mass number and taking away the neutrons that they're giving you, the number of neutrons. So there's 88 protons in radium. So all you need to do is that for for all of these different isotopes, and you find out that only D has 88 protons basically. 227 minus 139 is D. Sound wave travels from water into air. Its wavelength in air is longer than that in water. How does the frequency of the wave in air compare with the values in water? So frequency is the thing that's fixed. Whenever you get waves moving from one medium to another, frequency is fixed. It's a really important thing to get your head around. Okay, it's like, because then the same number of waves per second must hit the boundary, so the frequency is fixed. And that's why we describe colour as being a frequency rather than a wavelength. So it says, how do they in air compare in water? Well, it's faster in air than it is in water, so it's C. Red light refracts when it enters glass from air because its speed changes. So red light is replaced by blue light. So here's the red light doing it. Which statement is correct about the refraction of blue light? It's going to refract more than red. Okay, if you just kind of need to remember the kind of order of the spectrum. Red refracts less, and the reason for that is because the speed of glass is less. Speed in glass is less than red. Okay, which row increases the efficiency of a machine? So you just need to think, what does efficiency mean? There's loads in this paper about the definition of efficiency. Useful, the ratio of useful output over total input. I just remember useful over total. So if you increase energy due to friction, you're going to have less useful. So which one increases it? It's going to be one of these two. If you increase the output without changing the input, then you increase the efficiency, because the useful output, the fraction increases there. So the answer is D. Right, hockey player used pads on the legs to reduce injuries when hit by a ball. How do the pads affect the ball? So whenever you're thinking about padding, or importantly crumple zones in cars and everything, you think about Newton's second law. All safety features are about Newton's second law. You're basically decreasing the force because you are decreasing the acceleration. So the acceleration of the ball is reduced. Okay, that is how padding works. So this one, let's just have a quick look through. The acceleration of the ball is increased and the force is decreased. Well, that doesn't follow this law. The acceleration of the ball is decreased and the force is increased. Doesn't follow this law. The acceleration and force of the ball is increased. Okay, that does follow the law, but that would have a higher force, so it wouldn't be a very good padding. So here's more about radium-226. Decays to become radon-222. What is emitted when a nucleus of radium-226 decays? Well, it's got to be an alpha. So I've just written myself a little nuclear equation. I hope you can do these. Okay, essentially you start with this, it decays into this, and whatever's left over. So 226 equals 222 plus 4. 88 equals 86 plus 2. So it must be alpha, because we memorised that is our code for alpha. Be an alpha particle. Radioactive source has a half-life of 80 seconds. How long will it take for 7/8 of the source to decay? So in other words, if 7/8 have decayed, you have 1/8 left. So how many times do you have to times half by half to get an eighth? Well, that is 3 half-lives. So basically now you know the half-life is 80 seconds, 3 half-lives have passed, so 80 seconds times 3 gives you 240. Okay, the total 240 seconds, so that's C. There's a lot of misunderstandings about half-life, and this idea that a half-life is kind of half the time taken, it's the time taken for half the nuclei to decay. And then people think, well, that means in the same time you get the other half decaying, and so that's like its full life, if you like. But that is not the case. So after every single half-life, it decays by half. So if 4 half-lives have passed, then you tidy half times a half times a half, times a half. 4 times, a half to the power of 4 actually. Just bear with me, right? I'm going to have a little look at the chat. So if you've got any questions quickly, then just to say that there's some nice things, nice people saying some nice things here. But I just want to change the batteries in my little torch so that the visualizer looks better for you. So any questions? Thank you very much for some people saying that it's really helpful. Really glad to help, to be quite honest. Okay, it's makes me feel quite good. And I know it's late, but I really want to help you guys out because you've got your exam on Friday, and I know that it's quite a stressful experience. So this is why we're teachers. We like to help out. It was early in the paper, kinda, yeah. So they sometimes use the similar questions on the different papers, but they adapt them either to the tier or they adapt them to, in this case, to triple science. Anything else going on in the chat? Key points for discussion in fluids and upfrost. I don't think fluids and upfrost come into this one. Okay, fluids in OCR was in paper 1, but essentially an upfrost is caused by a pressure difference. So if there's a slightly higher pressure underneath an object when it's submerged, and so that means there's a resultant force upwards on the object. Battery. There's a resultant force upwards on the object, okay, and that resultant force is equal to the weight of water displaced. So essentially, upthrust is a force caused by being submerged in water. It's always upwards because of that pressure difference, and it's equal to the weight of water displaced. One way to think about it is kind of like the water trying to get back into where it was. Okay, the water didn't want to be displaced, it wanted to be there. So the force of it is equal to the weight of water displaced. And now it's still not going. Maybe there's a problem with it rather than. Oh, what a nuisance. Right, I guess I'll have to give in then, chaps, with that one. Okay, hopefully you can still see and you can still read this, but let's just crack on. Right, okay, so we're going to crack on with the visualizer stuff now. Okay, so a crowd makes a Mexican wave. A Mexican wave starts with people lifting and lowering their arms. So Mexican wave continues by people next to them lifting. Why is a Mexican wave an example of a transverse wave? Right, well, the oscillations are perpendicular to the wave direction. Okay, so the wave is moving in this direction and the oscillations are in this direction. So this is really just a different way of doing a do you know what a transverse wave is? Okay, so looking at the diagram, the frequency of the wave is 2 Hertz. What does this statement mean? So we don't need to do anything with the diagram yet, it's just asking us what's the frequency. 2 Hertz means 2 waves or 2 full cycles past a point in 1 second. Okay, so Hertz means per second. How many wave cycles per second? So how many seconds would it take the wave to travel 12 meters? So actually you need to do 2 calculations here. You first of all need to calculate the wave speed, and that's an equation you need to remember. Wave speed is frequency times wavelength. Okay, wavelength being 2 meters, and where did I get that from? That was from the diagram there. They've told you 6 meters from here to here. So how many full waves? 1, 2, 3 full waves. So the wavelength is 2 meters. So that's that. So you calculate your wave speed here, 4 meters per second. Then you use speed as distance over time to calculate the time. So rearrange for time gives distance over speed. 12 meters is from the question. Speed was 4 meters per second, so 3 seconds is your answers. Right. Goodbye to you. Okay. Ultrasound scans are used to produce images of tissues inside the body. Ultrasound scanner here is emitting and receiving the ultrasound. Ultrasound waves are emitted, they reflect from layers inside the body. Explain how the reflections are used to produce an image of the tissues. So basically it measures the time taken for the pulse to be received back. Okay, the time taken for the wave pulse to return is measured. The speed of the ultrasound in tissue is constant, or is known. Okay, so that's our important point there to make. We know the speed in the tissue, so we can simply do distance by doing speed multiplied by time. Okay. Now don't forget this point here, you have to divide that distance by 2 because it is the distance there and back. So don't forget that, there's that factor of 2. It's either the time for there and back, so divide that by 2, or you do the distance divided by 2. It's up to you how you want to do that. Here's a little table. You need to give X-rays, medical use, benefits and risks. You just need to fill in the 3 kind of gaps here. So another risk of X-rays is you can have mutations to DNA which could lead to cancer. You can talk about it damaging to living cells, but they've already done that, so make sure that you are adding value and you're doing something different to what they've already told you in the question. Okay, a good thing, a medical use of ultrasound is you can produce images of soft tissue. I guess you could have shake apart kidney stones as well, but this is the most obvious one. An example of a benefit is it's safe for use on prenatal scans. You cannot use X-rays on prenatal scans because those cells are going to multiply much more rapidly, and so it's much more likely to cause cancer. Okay, so this one is asking you, it's got a weight of 6,500 newtons and a potential energy of 217,000 joules. So how high above ground is it? Okay, this could be used as a potential energy is mgh, and you could work out that absolutely easily, but it's easier just to use this as a work done. So work done is force times distance, so rearrange for distance is work done over force. Plug the numbers in, there's my work done, the energy transferred basically, divided by the force, and I get this. Now this is what I read off on the calculator. Now I just wanted to make the point, always do some rounding. Okay, here 3 significant figures is good enough because they've given us 3 significant figures in the data. Just be careful when you do round that. If you round that to 33.3, you don't get that mark. You'd still get the mark for showing you're working, but you wouldn't get the mark for having it rounded. Okay, so 2 ways suggest, that's normally suggests, it's quite a hard question, fun enough, 2 ways to improve the efficiency of the roller coaster car. You can reduce the friction between the car and the track. So you're thinking, where is that energy going to go to? So energy due to heating, due to friction, reduce that. You could also make the car more streamlined to reduce drag. So again, be thinking about ways that you can reduce the heat loss. Okay, the information below shows information on radioisotopes. So here's some data. You've got a type of radiation, you've got the half-life, and you've got the penetration distance. So a doctor injects a patient with isotope C. Here we go, gamma, 7 hours, more than 10 meters, to track blood flow through the body. So it's using it as a radioactive tracer, in other words. Now, don't simply just copy down the data here. So if you were to say it's gamma radiation and it's a 7-hour half-life, you wouldn't get the mark, right? So use the data to suggest. So gamma rays penetrate the body. Notice we haven't been told that. If you just said they penetrate up to 10 meters, then you wouldn't get the mark. So it has to say that it comes out of the body so we can actually detect it outside the body, in other words. So the half-life, 7 hours, is long enough for the scan to happen, but it's short enough so it will not be radioactive for very long. So you won't go home radioactive, in other words. Right, so then the doctor talks about using isotope A, which is a few millimeters in size. So she intends to remove the isotope in a few weeks. Again, use the data to suggest 2 reasons why the doctor uses isotope A. So, alpha is very ionizing, okay? Now you don't have to say why that is, but I just want to give you the point that it kills more cells. Alpha has a short range, so that means it doesn't irradiate other cells near it in the body. Alpha has a longer half-life than D, okay, which is useful because she intends to use it again. Now how long is, alpha A has a longer half-life, 300 years. I guess she intends taking it out and reusing it then. Okay, so she's going to remove it, so these are the reasons why. Now you only need 2 of these, but these are the 3 possible marks, so any 2 of those will do. So again, not just the property, apply that property to the context that you've been given in the question. Okay, a doctor wants to irradiate a tumour using gamma rays. Why does the activity source need to be checked before it's used on the patient? Okay, the source or activity changes over time, in other words. Okay, so think about this. Gamma rays, why do we need to check it before it's used? Because the activity decays, it decreases over time. So we need to monitor to ensure we've got this correct dose that we want for our gamma ray treatment. We don't want it to be too weak, we don't want it to be too strong. Now, somebody earlier was asking for a redshift explaining Big Bang Theory, so here it is. Now I think they're going to give you these emission spectra in some ways, and you have to interpret them. Okay, so these are absorption spectra, all the colours with one line kind of missing where that wavelength of light has been absorbed. So when you get a 6-mark question like this, use the question to do a little plan, and I just suggest doing a plan like this. So use your knowledge of redshift. So that's my first thing. Basically, I'm going to bang down everything I know about redshift. Describe how the information in the diagram supports the idea of the Big Bang model. Okay, so I just need to say how it is. It's just a describe question. It should be pretty much straightforward. Put down my knowledge about redshift, apply it to the situation in the diagram. So firstly, redshift is a measure of the apparent change in wavelength of light due to relative movement between the observer and the source. Boom. Redshift, so basically the source is moving or the observer is moving, then there is an apparent and observed change in the wavelength of light. Redshifted light indicates the source is moving away. So if it's getting redshifted, then it's getting a longer wavelength. So that's because they're moving away. It's not because they're far away. We can infer they're far away, as we will do in a moment. Okay. So the wavelength is increasing. Red is a higher wavelength of light. The more redshifted the light is, the higher the recessional velocity is. So the recessional velocity means how fast it's going away from us, okay, and that's what Hubble measured basically using the redshift data. So these 3 absorption spectra, okay, you can see this is our star, this is the closest one, this is a nearby star, so it has been redshifted slightly, and this is a distant one, and it's been redshifted even more. So they're galaxies, but okay, same point. The 3 absorption spectra show the light from our star, the Sun, and nearby and distant galaxies. Okay, so this is just what it shows. The more distant galaxies are greater redshift. Therefore, more distant galaxies are moving away faster. And this is consistent. This is evidence for, I could have said, an expanding universe. And this is why it supports the idea of the Big Bang model, which has that point in it that the universe is expanding. Somebody just asked, can I explain redshift process? Imagine an object is emitting waves. Okay. Now if it is moving in this direction, then it gets closer to the waves that it's emitting, and it gets further away from the waves that it emits from behind it. So this is why we see a shorter wavelength here and a higher wavelength here. Alright, I hope that makes sense. Now you didn't need to do that because you didn't need to explain how redshift occurs in this question. But if you plan and then you check back through with the question, you just need to describe in this case. Okay, so Kate investigates how well balls bounce. Okay. She drops different balls from the same height and measures the height the balls bounce. She repeats the experiment 3 times. Now, you've probably done this as an efficiency experiment if you've done it at all. Okay, so here are the results. First of all, you see they're going to ask us to do that, and they work out the missing reading there. So here's how you do that. You basically work out what the total should be, and then work out what the individual reading was, so 28. So in other words, the mean was 26, so you do 26 times 3, and then from that you take away 26 and 24, and that leaves you with 28. So just 1 mark. Can you do some maths basically? It should be on a maths paper, I know that. Right. Okay, so Josh does an experiment with bouncing balls. Okay, he does an experiment with a drop height of 200 centimetres, and one ball bounces 100 centimetres, and he says this means it's a better bouncer than any of Kate's. Right. Now use your data and ideas about efficiency. So in other words, it's telling you to talk about efficiency to explain why Josh is incorrect. So basically this experiment says, well, as you know, the gravitational potential energy is mass times gravitational field strength times height. So in other words, potential energy is proportional to height. So this can be used as a comparison between the input energy and the output energy, or the total energy and, if you like, the useful. Right, so although they're not the energies, they're proportional to that, so we can use them to make that comparison. So this is me doing the highest one of the previous set of data. The highest bounce was 85, okay, on the averages here, and Okay, you could actually use any of those balls and this would work and you'd still get the mark. So I've worked out 85 over 100 gives me a fraction of 0.8 or decimal of 0.8, 85%, right? Josh's ball, so if you can just calculate efficiency, you get a mark. Josh's ball though, 100 over 200 gives him 0.5, 50%, so not as efficient. So my statement, my last mark is for saying Josh's ball is only 50% efficient, which is less than any of Kate's, so he's not correct. Josh uses a new ball. He says the ball is an amazing bouncer. He says if you drop it from 200 it will bounce to a height of 250. Explain why this is not possible. This is the law of conservation of energy. You can't get something for nothing. Energy cannot be created or destroyed. So you cannot have an efficiency of greater than 100%. That's impossible. Josh would need to add energy into the system to make this happen. Okay, so he's not got an amazing bouncer that is more efficient than 100%. Can't have more efficient than 100%. Alex has 2 radiators in her home. They're filled with 10 kilograms of different liquids. The radiators are different power ratings. Well, I know it did take me a little while because there's so much data in this question to work out what to do. The heaters are turned on, the temperature each rises by 40 centimeters. Right, now I've got a clue, haven't I? Because I know there's only one equation I know of which has got a temperature rise in it, so I'm going to bang that down. In 1,680 seconds. Okay, so I can probably work out an energy from energy is mass times specific heat capacity times temperature change. And if I've got time, then I've got power, then I can probably do some comparisons there, can't I? So my first step is just for oil, this is this bit, and for water, I'm going to calculate the energy rise, right? So here it is, 10 kilograms, 1,680 is the specific heat capacity for oil, and temperature change of 40. Same for the water, but instead it's 4,200 is specific heat capacity, 40 degrees change as well. Here's my energy for water, here's my energy for oil calculated. I've already got 2 marks pretty much. Then the second step of this calculation, this is the trickiest ones in both OCR and AQA, all the things, they're asking you to do 2-step calculations. So then you have to figure out, well, use the data to show the same time. So I have to calculate time. Now I've got energy and I've got powers, and I know they're related together by this equation. Power is the rate of transfer of energy, power is energy over time. I can rearrange for time and I get energy over power. So use this energy and its power, 400 watts. Use this energy and its power, 1000 watts, and I get the same time. So basically remembering and applying this equation by rearranging it correctly and then having the same numbers, 1,680. Okay. Okay, Alex has 2 fires in her home, X and Y shown in the diagrams. Right. So these look like very complicated, but they're actually very simple kind of Sankey diagrams. Right. Here's the fires, here's the room, and here's the chimneys. Okay, so take your time to understand those. Just don't panic. Okay, just take your time to digest what's in the diagrams. Why does Firewire save money on the energy bills for her home? Use calculations of efficiency in the answer. So it's already told me to calculate some efficiency. So here we go again, efficiency. Efficiency is useful over total. So this one does 4 kilowatts to the room, that's useful. Total 5 kilowatts input, so this is 80% efficient. 4 kilowatts to the room, 5 kilowatts input to the fire, so that's 80 as well. Oh, no it's not, because actually there's a second energy pathway here, which is 0.5 kilowatts to the cold water in the heating system. So actually, we're using some of the extra energy to heat up some water, and that means that's the energy we would otherwise have to pay for, right? So we had 1 kilowatt going this way in a less efficient one, and now we've got half a kilowatt this way. Okay, so some energy from this fire goes to the heat exchanger, and I've worked out how much, and I've stated it down there. It's just in the margin. You'll need to write in the box. This one doesn't have boxes because it's a specimen paper. So I've got my marks for doing the efficiency so far. I've got my mark for saying some of that energy has gone to the heat exchanger, and this is more useful, so less energy. This is more useful energy, I should put. So less energy needed to heat the water in the central heating system. So this essentially is talking about less energy we need to pay for otherwise in the central heating system. So the bills are lower. Okay. State 2 features of a satellite in a polar orbit. Okay. Orbits, I've actually done more than I need to, okay? So it says state 2 features in the satellite in a polar orbit, and I almost made an error because, look, there's a second part to this, suggest a use for the satellite in polar orbits. Now, if you do as I do and you look for the command words, then you will make sure you don't miss those things out. So state 2 features, but 3 marks. Oh yeah, look, there's another point. There's another part to this question. So what is it with polar orbit? Well, it orbits over the poles, funny enough, and it orbits at a higher speed. So you only need 2, but here's the other ones you could have. It's lower, at lower altitude maybe. Okay, it's multiple orbits per day, and it covers the entire Earth. Okay, even like one day, it doesn't stay over the same place. So it's very useful, and you only need one of these. Suggest a use for a satellite for mapping, or for weather, or for spying. Okay, surveillance satellites. An artificial satellite X is kept in a stable circular orbit by a centripetal force caused by gravity. Centripetal force always towards the center of a circle. Explain how the velocity of the satellite is constantly changing whilst its speed remains the same when it's in orbit. Okay, so explain this. Well, basically, so you don't need to say it is changing, you need to say why it's changing, right? Well, velocity is speed and direction, is in a given direction. So firstly, it's just identifying, velocity is vector, it has direction. Direction is constantly changing, so the velocity is constantly changing is the second mark. The satellite is remotely controlled from Earth. The scientists want the satellite to move slower. What effect will this change in speed have on the height of its orbit? Explain your answer. So if it's going less fast, then it's going to actually increase in height of orbit. Okay, they'll need to boost it to get up. They'll need to give it energy to get it up there. But actually, higher orbits have lower speeds, and that's really what this question is asking about. Okay, it's not about it falling down to Earth. We can get it up there. We can put the energy to it. But a higher orbit has a lower speed, and you just need to memorize that. So why is this though? Explain it. This is the second part of the question. Look, there's less force needed for lower centripetal acceleration. Okay, so in other words, it's higher up, so you don't need as much force needed because it's further away from Earth, so it's a lower speed. The diagram below shows the structure of a transformer. Primary and secondary coil as we used to. It's a step-down transformer, although that's not the answer to any of the questions. Okay, the point is there's fewer turns on here. Explain why there's more alternating current in the secondary than in the first. So the voltage has reduced, therefore the current increases. Okay, why is that though? There are fewer turns in a secondary coil than the primary. So lower potential difference is induced. Okay, so this is the lower potential difference there. Lower potential difference gives a higher current, as power on the primary is equal to power on the secondary. So VI on this side is equal to VI on that side. If voltage increases, current has to reduce to allow this to be the same. The last mark. You don't need to quote the equation, but you see it's a really useful equation for explaining with transformers and how step-up transformers increase current but step-up transformers increase voltage but reduce current. The secondary coil produces an output of 12 volts, we're given that on here. Calculate the number of turns needed on the secondary coil and show your working. So you're given primary voltage, primary turns, and you're given secondary voltage. And you need to work out secondary turns. Okay, so here's the transformer equation. Voltage on the primary over voltage on the secondary is equal to the number of turns on the primary over the number of turns on the secondary. Put in all the numbers where they go, and you just have to make this fraction equal this fraction. So there's loads of ways of doing that. All right, the way I do it is, well, I'll move this to the top of a new fraction, and therefore I'll do this over this fraction, basically. And I'll type that into the calculator nice and carefully. 27600 fraction 230 divided by 12. Boom. Okay, and it gives me 1440 turns. You don't need to put the unit on turns because it's just a number. But all you really need to think about is how did I get from that to that? And it's the same way to get from that to that. Okay, so you can check this by making sure that the fractions are the same. 230, how do you get to 12? You divide it by whatever 230 divided by 12 is. Okay. Another question with the transform of power equation. So they're really going to town on this one out here, aren't they? Right. So voltage increase before transmission from the national grid from 25,000 to 400,000. This increases the voltage 16 times. How much would the increase in voltage affect the current? The current would be 16 times lower. First mark. Why? Because power is conserved. Voltage on the primary times current on the primary is equal to voltage on the secondary times current on the secondary. We've told you to use this formula, not to do a calculation, to do an explanation, and this formula is often used in explanations as well. Right, so firstly, the point is that power is influenced by current. Lower current, lower power. But because power is equal to current squared times resistance, or in other words, power is proportional to current squared here, if we halve the current, we get a quarter the power. So that's what I basically said here in words. So lower current gives much lower power. Power loss, we call this, okay, so we often remember this equation as being the power loss equation. Power loss equals I squared R. So you get much less heating effect of current. So power is proportional to I squared R, so if current halves, power is a quarter of what it was. And you do need to, where possible, get a quantitative analysis in there, okay, so a quantitative comparison, either talking about proportionality, or in that case, proportional to something squared. Right, so Matt experiments with radioactive materials. I hope he's been supervised during that. He investigates how the activity of radiation changes with distance. The radiation moves from the source to the detector, so he's moving this away from it basically. He measures the counts per minute from a radioactive source. Table shows the results from the experiments. Okay, so 10, 20, 40, 80. Right, so each of these are doubling. Look what's happening over here. Well, each of these are quartering, if you like. So to get from here to here, you times by 2. Here to here, you divide by 4. So that's the analysis that we can do. Doubling the distance reduces count rate by a factor of 4. That gets me both marks. I think in this type of question, if you just said further away, lower count rate, you might get 1. But we can do the analysis with the data, right? In other words, count rate is proportional to the inverse square of the distance. Okay, that's a neater way of saying it, I think. Although not looking for you in this OCR Gateway to have that kind of words in your vocabulary, they're just looking for you to be able to recognise a pattern in this case. They talk about that in the biology OCR Gateway, don't they? So it's something that you can talk about. It is correct. Okay, so Matt does 2 further readings. Here they are. Okay, his results are in the table. They aren't following the pattern, are they? Right. So as the difference is increased to 160 to 320, the results do not follow the same pattern as the others. What do you think these results should have been? So that's the first part. Explain the anomalies in the last 2 results. So 160 should be 4 because that's doubled. So that should be divided by 4. Okay. So that should be 16 divided by 4 is 4. And this should therefore be 1 because again that's doubled. And that should be therefore divided by 4. So that should be 1, and I've just said that in words there. So that's the first mark. Explain the anomalies in the last 2 results. Well, it's because radioactivity is completely random, and so we can't predict exactly which radioactive nuclei will decay when. So in other words, we cannot predict what count rate you're going to get. It doesn't follow any kind of perfectly predictable pattern. The point is, over very large numbers, you get very predictable data, the law of kind of averages. If you roll a dice 100 times, then you'll get 1/6 of those will be 6s, right? As numbers are very small, the effects of random errors are much more noticeable. So the point I'm making here is that these numbers are way too small to see the exact pattern that we were expecting. Okay. Now, I did think when I first saw this one, I thought, well, this is because of background radiation, but it's not background radiation. And why? Because if it was background effects, okay, these numbers would be higher than we would expect them to be, not lower than what we'd expect them to be. So gamma radiation is used to irradiate cancers in the brain. Treatment is used for 15 minutes every 4 days. Each patient receives a certain dose of radiation. Gamma ray sources rotate 360 degrees around the head. Patient remains still during the treatment. Explain how this treatment reduces damage to healthy cells. So the gamma source is rotated around the tumour. So this limits the dose to the healthy cells. Okay, that's the first thing. So in other words, in the gamma gamma ray things, right? Okay, we've basically got the tumour in the middle of the head, and we rotate the gamma ray right around. We draw the rest of the head on there. Okay, so it's always focused on the tumour, but the healthy cells don't get a focused dose. So this limits the dose to the healthy cells. So this, why does it limit the dose? Because the healthy cells are irradiated for less time. There's two ways of escaping radiation, if you like: distance and time. You want to be irradiated for as little time as possible, and you want to be as far away as possible. Okay, but these don't. They want to have the right dose on the tumour and less dose on the actual healthy cells. So the patient undergoes a treatment. So then I was thinking, well, what else? That's it, isn't it? That's how they limit healthy cells. That's my normal 2 marker. Explain how gamma knives, radiotherapy, limit the dose onto the healthy cells, rotating around. But there's other clues in there to the next 2 marks, right? So the patient remains still during the treatment. Okay, so that means the healthy cells don't get exposed any more than they need to. So if you move around, then you're going to move in those healthy cells more often through the beam. That's one clue. And the next clue is they're 15 minutes every 4 days, not an hour all at once. So this undergoes treatment at 4-day intervals, so healthy cells have time to repair. Last question now then, okay, back onto stopping distances in cars, safety in cars, and using the data again, and you've got to fill in the last data, okay, the missing information at speed of 32 meters per second. So again, look for the patterns, right? So when the speed of the car doubles, the thinking distance doubles, okay, and that is always the case if we look through the data. The braking distance though increases by 4, and again that is the case if we look through the data. The total stopping distance is always this plus this. Okay, now that should be something that you know, but also you can get that from the thing. So all you need to do, you've noticed this is times 2, so this must be times 4, 96. This is times 2, so this must be 96 plus 24, 120. So mark for this, mark for this. Look at the graph, the car starts to brake and then stopping. Use the graph to show the braking distance. This braking distance we want is 6 meters. Okay, so this is the thinking distance, and this is the braking distance, and this is the total stopping distance, will be the area under the whole thing. We just asked for the braking distance, so it's just the area under the triangle. So you do a half times 8 times the base. Okay, half base times height. 6 meters is the total distance. All right, that's 1 mark for recognizing area under a triangle. Basically, area under a velocity time graph is the distance traveled. Formula to work out kinetic energy is half mass times velocity squared. A car has 30,000 joules of energy and a mass of 1 ton. Okay, so 1 ton is 1,000 kilograms, and that's what you need to use. That's the SI unit of mass, so make sure you use it in your calculations. Calculate the velocity of the car and show your working. So I've done the rearranging first. Okay, kinetic energy is half mv squared. Memorize that. So times by 2 and divide by mass gives us 2ek is over m is v squared, and then root both sides to give you v equals root 2ek over m. I suggest you remember that, okay, and then you don't need to do that rearranging in the exam. So root of all of this, okay, 2 times 30,000 divided by 1,000, and then root it, and I get this all on the calculator. And again, I'm making the point, do some rounding. I'm happy with 3 sig figs, okay, there is no rounding mark for this one, doesn't tell you what to do, but 3 sig figs is normally fine. Just be careful, because again 7.74 is not correct.